So this is a 32-bit integer, and if I divide any integer by a power of 2, then that's just like erasing the lowest order bits. And how many bits do I erase? It's whatever the power is. Okay, so in this case, here, somewhere around here starts the lowest order 16 bits. I just forget about those, and I only care about the highest order 16. So the answer to this question, even though I can't tell you what the number is because I can't do, I can't read binary numbers that fast. Hope I counted that right. It would be this 16-bit binary number. All right, so this is a 32-bit number, which means it's in the range 0 up to 2 to the 32 minus 1. In this case, I can rule it down a little bit because the highest order bit was a 0, so it's really only up to 2 to the 31 minus 1. But in general, 32-bit number gives you something in this range. And so this is just a sort of another way of looking at what we did last class. So last class, we were studying Van M. de Boas trees. And remember, so Van M. de Boas tree was made for storing integers from a set like this. All right, and we called this number 2 to the 32, we called that n. And at a very high level, what we were doing with Van M. de Boas trees is everyone had root n children. And then there was this other ox thing of size, also of size of root n. And you may remember in that, in the code for that, there was some line in there that says I gets x divided by square root n floor. Okay, so if n is 2 to the 32, square root n is 2 to the 32 to the half, which is 2 to the 16. So that division in this case is doing something like this. It's keeping the highest half part of the bits. And then you may or may not remember the details, but somehow we made a decision in constant time where basically the search would either search in ox and we were done, or it would go into one of the children and search there. So what's really happening, so if we searched in ox, we were searching for I, which means we were searching for this value of these 16 highest bits. And if we searched in the child, then although the code said we were searching for x, actually the only thing that we would use ever are these lowest order 16 bits. Okay. So one way to think of Van M. de Boas trees and what's happening is that the structure is organized in such a way that you have enough information to make a decision about whether or not these low order bits matter. Okay. So if we go searching in ox, it turns out we never looked at these low order bits again. They didn't matter. And if we go searching in this lower tree, well, then the higher order bits don't matter anymore. We use them to know which tree we're searching in, but after that, they go away. And then if you think about, well, what's ox? I mean, the search can go one of two ways. It can go recursively into the subtree, in which case it's working on here, or it can go recursively into aux, in which case it's working with these things. But aux is just, again, recursively a Van de Boas tree. So when I search in it, it's going to make the same kind of decision where it's going to look at the highest and lowest order 8 bits and decide whether or not the high order bits are the important ones or whether or not the low order bits are the important ones. So it's kind of like it's doing a binary search, but the binary search is somehow on the location which really matters for where we're going to find this integer. So that's a really high level view of what's happening with Van de Boas trees. So today we're going to look at, when you think about Van de Boas trees this way, some versions of those that look, I mean, they look different from the outside, but if you think about what's happening in Van de Boas trees, you'll realize maybe these things are not so different, even though they came 25 years later. But we'll start with, well, we'll start with a reminder. So the operations we were doing were insert, remove, and successor. And somehow the thing that makes this difficult is the fact that we want to do successors, because you have probably seen things that are implemented as hash tables which support insert, remove, and a third search operation, which is sometimes called contains, tells us whether or not X is in there. It's sometimes called get, or maybe find. But the difference between these operations and the successor operation is that these operations only give you useful information, well, these two anyway, only give you anything useful if the value X is in the set that you're storing. So contains will tell you whether or not the value X is there, so it returns true or false if X is in the set or not. But get and find, they will they'll give you the value X back, or the record, the data associated with X, if it's there. And if X is not there, they don't give you anything useful. They just say, no, it's not there. Successor is different, right? Because when I search for X and I ask for its successor, even if X is not there, I will still get the next value that's just the smallest thing, which is larger than X. And these turn out to be quite a bit easier. You may have seen, and we'll see again in this course, efficient implementations of these, but this is what hash tables do. And even the simplest ones can do this in constant expected time. Okay. So if you don't care about what happens, if you don't care about searches for things that are not in the set, you just want the answer that they're not in the set, then you can do everything in constant time. And I don't know, a lot of people don't realize this. And I think that's the fault of computer science educators, because hash tables are not that much fun to teach. There's much more sort of interesting ideas in things like binary search trees and skip lists and so on. And so students leave with a computer science degree thinking that, well, if you want to store things and be able to search for them, you use binary search trees. And they don't think about this later when it comes time to implement things, and they don't think about whether or not their application actually, whether it makes sense to even search for things that are not there. So you'll see people using binary search trees and then only using the contains operation on those binary search trees. It's a bad idea. Use a hash table instead. Everything will run in constant time instead of log n time. But for now, let's just remember we can do these things. And in particular, the one that I'm interested in is the one in Java, what's it called? The map class has a function called get that lets you store values, and then retrieve them. So you store pairs of things. One is called the key, that's the X. The other one is called the value. And later, after I've stored it, I can ask you for the value associated with X, and you get that in constant expected time. We're going to use that. Sort of like arrays. I mean, arrays can do that, but only in the case where X is an integer between 0 and the length of the array minus 1. Hash tables kind of extend that to arbitrarily big integers. All right. But let's start with something really simple first. And this is the binary trie. And some of you, if you have taken data structures with me, are going to have seen this before. Sorry about that. It's usually taught at the end of the course because it is advanced material, not typically taught in an undergrad course. So this may be a review for you, but most of you, I think, are not in that position. So what's a binary trie? A binary trie is just a tree. And I should say that actually the way you pronounce this word is actually tree, but then it's confusing because I'm going to talk about trees and I'm going to talk about these things. So I'll call this trie, but the true pronunciation is tree. It's part of the word retrieval historically. All right, so what's a binary trie look like? Well, it's a tree in which all the leaves have the same depth, and all the edges, you know, if a node has a left child, it's labeled with a 0. If it has a right child, it's labeled with a 1. And all the leaves are at the same depth. So let's do this. And each leaf represents the integer, which is that you get by stringing together this sequence of zeros and ones, right? So this is the integer 1, 1, 1, or 7. This is the integer 0, 0, 0. That's 0. This is 1. This is 2. This one is 4. And that's it. Okay. And the way you so let's think about what we're looking at. We're trying to store a set of just like we were doing with Venom-de Boas trees. We're trying to store a set of integers so that we can add, remove, and do successor search. We'll be more explicit here. Venom-de Boas trees said when we talked about those, we said they were from a set of size capital N. But let's just be explicit here and say that they're from a set that looks like this. Okay. So n is 2 to the w, so they're w-bit integers. So that means the height of this thing is going to be W. And another way to look at, well, what's W? W is also log of the thing that we used to call n. All right, so it's a tree of height log n. And if it stores some integer, then there is a path in the tree from the root to a leaf that stores that integer. Okay. I mean, that path represents that integer. So we'll do a couple of things. One of them is these leaf nodes. We'll link them into a doubly linked list. All right. So that's one thing that we'll do. And the other thing that we will do is at each of these internal nodes, maybe this isn't a great example, so let me erase something from it here. At each of these internal nodes, if the node doesn't have two children, we'll do something with the pointer that's that would have normally been pointing to that other child, the missing child. And we will have it point to, let's say, the next thing in the sort of the next largest value. Okay, so what does that mean? Well, it's kind of natural when you see the tree shape here that any value that I would get by going off to the right child here is actually going to be between this number and this number. So it doesn't matter what path I happen to take, it's always going to be between these two numbers. So we'll point, let's say we're trying to do successor search, so we'll point to the larger of those things. Okay. So that will have that. Here is another one of those nodes that only has one child. So it'll point over to here. And here's another one of those nodes that only has one child. It'll point over to there. Okay. All right. So that's the binary trie. And how do we search in a binary trie? Well, we have some number we want to look for. Let's say we want to look for 011. That's gone now. 011. So we start at the root. The first bit of the number we're searching for is a 0, and the root has a child 0 edge, so we follow that. The next number we're searching for is a 1. The root does not have a child, an edge to a child labeled 1. Instead, it has one of these jump pointers. And when that happens, well, that jump pointer will actually point to the answer. So the jump pointer points to the successor. Okay. So the searches are easy. Either you make it all the way down to a leaf, in which case the answer is the value you're searching for, the value x you're searching for is there in the set. And if there's any data associated with it, it would be stored down at this leaf. Or you don't make it. Instead, the search tries to take you out of the tree by following a child pointer that's not there, in which case you follow the jump pointer instead, and it immediately takes you to the answer. Okay. All right. So that's how you do a search. And well, what about adding things or removing things? So first of all, don't be, you may have a question mark over your head wondering why are we doing this? That search, as I just described it, takes time W, and W is log n, and that's last class we were seeing search times of the form log n. And in fact, if you think about this even more, n is the total number of values you're allowed to store no matter what. So this could never be better than just storing everything in a binary search tree, because the size of your set, the subset of this, is not more than capital N. It's actually what we'll denote as little n. And a binary search tree could search in log little n time, and little n is always not bigger than big N. So that's disappointing, but the point is to build up from here. Okay, so searching in this thing takes O of log n time. Okay, and what if we want to add something? Well, let's go with our running example. Let's say we want to add, or I want to add 0, 1, 0. Okay, so probably the easiest way to do that is to first search for it. And when we search for it, well, we go 0, and then we try to follow 1. We don't find it. Instead, we find its successor. So we'll just remember that for a second. And then now back up. Now we know the successor of the thing that we're trying to add. Now back up and start again and really add it this time. So we start searching until we start to fall out of this tree. At this point, it's time to start really adding something. So the jump pointer at this node is going to go away because it's about to get its second child. So we put that in there. And all right, so that's the 1. And then we need to put in the 0. We put that in there. So there's our node, 0, 1, 0. And we have a successor stored for that node all the time we're doing this. So we know, well, we can insert this thing into the doubly linked list. It's going to go just before that successor. And actually, we have more than that. From this point on, once we started creating this path, each of these nodes will only have one child. So it also needs to have a jump pointer. And that jump pointer is either going to be, well, in this example, this is a 0. So the jump pointer is just going to be to this successor. Or we don't see it here, but if the path did a, well, something like this, then the jump pointers everywhere that this path you're inserting turns right, their jump pointers will point to the new thing that you're inserting. Okay. All right. What's that? Yes. Yeah. So there's a path. We should be really specific here. So here's this new path that we are creating. And there is a path that was there before, maybe something like this. And well, some of the nodes on that path may be missing their right child, in which case their jump pointers used to point over here to this thing. They should be updated to point here. So I guess the cleanest way to do that is create the path, splice it into this list here, walk back up, adjusting these jump pointers, and from this point on, you can walk down and fix these jump pointers. So you can probably do it more efficiently than that. In fact, if you look at the notes, there's code for it. Okay, so, but in any case, that's down the tree once and then back up once and then down again. I mean, it's a constant number of passes up and down this tree. So you can add of log n time. Again, nothing to get excited about. And what about removing? Well, I mean, let's just remove something and see what we need to fix. So to remove something, well, if you're removing it, it's there, or you can assume that it's going to be there. So you search for it, you will find it at a leaf, and you're going to get rid of that thing. And you're going to walk back up this path, getting rid of any node which only has one child now. So for instance, this node now, or yeah, in fact, any node that has no children now. So this node now has no child, you get rid of it. This node has one child, you stop there. And then there's a bunch of jump pointers that you need to fix. Where are those? Well, they will be on the sort of leftmost path, starting from here, the leftmost path, and then on this wall from here. So that's going to look like this. And there were some over here that pointed to this thing. In fact, this one here. And you can do that because the node that they're all going to point, I mean, they all pointed to this, which you just deleted. So now they're all going to point to the next thing that's bigger than this, which was the next thing in the linked list after this. So that also takes log n time. And sort and remove. Not at all exciting. All right, so that's a binary try. Here comes another second data structure we want to look at as a variant of this called the X-fast try. And the X-fast try, we're going to not try to do everything at once. We're just going to try and speed up this search time. So we, instead of having searches run in log n time, we would like them to run in log n time. And so let's think a little bit about search in a binary try. At a very abstract sense, the search starts at the root and follows a path for a while until it steps off out of the tree. And the moment that happens, the search is done, because this thing has a jump pointer which points to the answer. Okay. So actually, it's good when, I mean, the The sooner this happens, the better. In fact, what we would like is, well, right now, what's happening is we're finding the node where this happens, and the way we're finding it is by starting at the root and walking until we find it. And that takes W steps. We would like to find it instead in log W steps. So that means this strategy of walking and checking this thing one at a time is not going to work. Instead, we want something like binary search. All right. Let's think about this for a minute. These, I said that the leaves here correspond to the integer, which is you get by stringing together the ones and the zeros. But it's not just the leaves, right? Like at the root here, this thing is sort of the empty string. There's nothing there yet. But this is the string 1. And this one here is the string 1, 0. And this one here is the string 1, 0, 1, 0, 1. All right. And clearly, if this is the way my search went, then what happened is I was looking for a string that started with 1, 0, 1, 0. And it was on this 0, I tried to follow this thing, but I couldn't. And that's when the search ended. So all right, and then this string had more stuff in it. So if I look at each of these levels of the tree, there's a set of strings associated with that level. Like, you know, let's be explicit here and tell you what they are. At level 0, there's one string, it's the empty string. At this level, there's a 0 string and there's a 1 string. At this level, there's a 0, 0 string, there's a 0, 1 string, there's a 1, 0, and a 1, 1. And, oh no, there's no, oh yeah. No, there's no 1, 0. There's only these things. And then at the bottom level, well, there's the list of strings there that are at the bottom level. Okay, good. So when I go looking for 1, 0, let's say 1, 0, anything, I fall out here because at the second level, there's no 1, 0, right? 1, 0 is not in this set. Okay. So that means that I fall out. I didn't fall out up here because 1 was in the set. And you never fall out up here, really. So somehow that tells me that, and in fact, it doesn't matter what else I put here, 1, 0, 1 or 1, 0, 0, but it doesn't matter which one I'm searching for. Because 1, 0 is not in this set, then 1, 0, 1 is not down here, and 1, 0, 0 is not down here. Okay, so right, this basically says I can when I search for this thing, I can only find whatever, the first bit, and then I fall out. And then after that, so that means I'll never find anything that starts with a 1, 0. And the same thing here. This is the string that was 1, 0, 1, 0, and I fell out when trying to match that 0. That means there's no string that starts with 1, 0, 1, 0 here. And in particular, if I go to the middle level, this is level like W over 2, there's going to be no string that starts with this. All right. So basically, I want to know, I want to find the first place that this search falls out of the tree. And I now have a test for that to know whether some level is below that, so that it fell out of the tree before, or it fell out of the tree, it's still in the tree at this point, right? So I can go to the middle level and ask, take my string, take the W over 2 highest bits, and say, is there a node at the middle level that has this label? If the answer is yes, that means I could have followed a path right to that node. I would have succeeded. If the answer is no, that means that the place that I'm looking for where the search would fall out of the tree happens before. Okay. So that's what we want, right? You take, you get a test that says the answer you're looking for depends only on these first W over 2 bits, or the thing you're looking for is somewhere dependent on these last W over 2 bits. In either case, you've narrowed down the range by a factor of 2. Okay. Now, how do we do that? How do we, how can we ask across a whole level whether or not this string 1010XX appears? We do what? No, we don't make another try for each level. Yeah. Yeah. So the question we're asking at one of these levels, it's not a successor search. We're just asking, is there a node here at this level that has that label? If the answer is no, I just want to know that the answer is no, because that means I only need to look up top. If the answer is yes, then it turns out that it'll actually be useful to give me the node with that label. But that's hash tables support that. That's the get operation in a hash table. Okay. So an XFast try is a fancy sounding thing, but it's just a binary try in which at each level you have a hash table that stores the strings, or I mean, they're binary strings, which means they're just integers, and if you interpret them that way, the strings that are associated with the nodes at that level. Yep. Sorry, which? Yeah. Okay, so if you do, I mean, if you complete this search, what you will find is 2 consecutive levels where I mean, you'll find a level here where the answer is no, and then you'll find the level just above it where the answer is yes. And in the level just above it, well, the answer is yes. So the hash table can tell you which node has that label, and that node has the jump pointer that takes you to the answer. Does that answer your? Is that what you're asking about? So well, so the search now is log W searches. I mean, you have to look at log W levels, because each time you look at a level, you're cutting the range in half. And each of those things is a search in a hash table, which takes constant time. So in total, that's only of log W time. Oh yeah, that's easy. That's so because we've been doing this already. We've already been doing math with our indices, the things we're looking for. So the string we want to search for, you can get just by well, you can think of it as dividing by 2 to the W over 2, or by right shifting by W over 2. Okay, so that's not a problem. And I mean, what you're always searching for is some prefix of the string that you're given, and you can always get that prefix just by right shifting off the parts you don't care about. Yep. Okay, so space complexity doesn't really increase asymptotically, because what have we done here? Well, we've still got the binary trie, and it has a leaf for every value that we store. So the number of leaves in this thing is little n. So the little n, that's the number of things actually in our set. And while each of those leaves has a path leading up of length w, so the space is not more than n times w. Okay. And that's, I mean, that's not a small thing, but let's remember it now. We'll fix that later. Because that's the same thing as saying n times log big N. But adding the hash tables doesn't increase that at all, because all the hash tables do is they store, I mean, they basically store the nodes at each level, and the nodes are already there. All right. And actually, if you think about it for a little bit, you sort of maybe realize, do we really need the tree at all? Do we need the left and right pointers? Are we using them anywhere? Somehow the whole tree is implicit in this sequence of hash tables that we have. But don't worry about that for now. It's still good to think of this tree as being there. Okay. And well, that's great. So the search in an XFast try runs in O of log n time, which is O of log W time. That's just like in a Venom de Boas tree, but you'll see that these things are still going to be slow. And there's not really any way around that, and it comes from this question you asked about the space complexity. The space is little n log big N, or little n times W. And well, that means that if I do n insertions, I'm building a structure of size n log n, so on average, each insertion has to cost log n. So the space and the time to do insertions, those two things are closely related. And the fact that the space is too big means that the insertion time is going to be bigger than we want. All right. So any questions so far? Yeah. As a separate structure off to the side. So, and exactly how you want to do that is you can have one big hash table that stores all the strings associated with all of the nodes. Right, that's fine. The strings at this level are all different than the strings at this level because they have different lengths. So that comes for free. Or you can break it out into separate hash tables for each level. But if you think about it for a little while, you'll realize there's not really any need for the nodes, because what are you ever going to use for a node? You're not following you're not following child pointers anymore. The only thing you're ever going to do is when you finally find that node, the lowest one on that path, you're just going to look at its jump pointer. So really, all you've got is a giant hash table that's mapping these binary strings onto jump pointers, which are just a pointer into a linked list at the bottom. All right. But I mean, there's still the updating of jump pointers, which you can also do with the hash tables. Although then, instead of just doing simple pointer, I mean, walking up the tree and updating things, you keep having to do lookups in hash tables, which may or may not be the fastest way to do things. So depends how you want to implement it. But so you can store the tree or not. You can get away without it if you really cared about the space, but it makes it somehow probably faster to store it explicitly, just because of this walking up and down and fixing up the jump pointers everywhere. All right. So that's, what do we have so far? We've seen binary try, which does everything in log n time, disappointingly. And we have seen xfast try, which is just a binary try augmented with hash tables for the nodes. That does searches in log n time. And then the final answer is what's called a y-fast try. That's going to try and get these things down to log n time, and simultaneously, because it has to, it's going to get the space down. And it's going to get the space down to O over little n, not little n log n, which is actually better than Van M. de Boas trees. Okay, so all that, but let's pause for 1 second, because this xfast try, there's a lesson here, which is what we did, the way it works, the first step in a search is to go straight to the middle level, look for these first highest order W over 2 bits, and then make a decision in constant time about whether the thing we're looking for is determined by these highest order bits because it's in the top part of the try, or whether we need to keep looking in the lowest order bits because it's in the bottom part of the try. Think about the Van M. de Boas tree. There, we made some decision and decided whether we would just look in the aux table for the highest order bits, or whether we would have to go into a child and look for the lowest order bits in there. So these things are not so different, even though the explanation, I mean, on the surface, they look quite different. Okay, y-fast try. This actually is nice because now we're going to, it illustrates a really common technique, one that we're going to use a couple of times next week as well, that has, it's not a dirty trick like some of these things are, in the sense that hashing is somehow this trick of beating up an integer and doing something with it. I mean, it's an array lookup trick. But this next trick, it's They call it indirection, but it's applicable in a whole bunch of settings, and it's a trick that you often use to save space. So let's treat our XFAST try as a black box. We have this data structure that can do searches in loglog n time, but inserting and removing still takes log n time. So we're going to use that. Call that thing X, because it's an XFAST try. But what we want to do now is just not have to, when we insert into our we have a big data structure, something more than this, that contains an XFAST try, and we want to avoid inserting and removing from the XFAST try as much as possible. Okay. So remember, at the bottom of the XFAST try is this doubly linked list that has the values in there. And actually, remember the space on the XFAST try is also too big. So we can't actually even store all our stuff in it. So somehow a lot of stuff is going to have to live outside of it and not be in the XFAST try. In fact, we want the whole thing to have O of n space. So this thing here should have only something like n divided by w things inside it. The rest has to go somewhere else. So only one out of w things is allowed to go up here. All right. So at the bottom then of this XFAST try is going to be this list of n over w things, but we're trying to store n things. So, what should we do with those remaining things, which is actually the majority of them? Well, we can't just store them in the hash table because hash tables won't help us with successor search. But I mean, we get to store something in here. Like in this XFAST tree, we can store 1 out of w things in there. So if I'm going to pick the stuff to put in this thing up here, but I'm only allowed to take 1 out of w of them, should I take the smallest n over w? Should I take the largest n over w? Yeah. So if I'm only allowed to keep 1 out of every w, then that's what I'll do. I'll skip the first w minus 1 and then take 1. Skip the next w minus 1 and then put 1 in there. Skip the next w minus 1 and put 1 in there. So that means if these are the things in my that are actually stored in the XFAST try, the things that are not in the XFAST try, well, they're broken up into little groups here. And if this was perfect, if I could really do this perfectly, if I really took exactly 1 out of every w, then each of these groups would have size w minus 1. Right. The first w minus 1 smallest things, and then this one goes up in the XFAST try, and then the next, and so on. Okay. So it's going to be hard for me to maintain every group exactly the same size. We'll deal with that in a second. But let's say that that's not a problem for now. How am I, so is this going to be good enough? Is this going to work? Well, So let's say I come searching for some value x. So I go looking in my x fast try, and it says, okay, well, successor of x is here. And this is a doubly linked list, so that means the predecessor of x is here. Now, I'm not done because that was only searching in the sample of 1 out of w things. I don't want to search in the whole thing. But I've certainly narrowed down my range. In fact, I know that the successor of x is either this one or it's in here. Now, this is really small. There's only w things in here. And I'm only aiming for a search time of log w, which is log n. So I don't need any fancy structure here. Binary search tree will do. Okay. So here you can just take a binary search tree of size. I'm writing w minus 1, but that's going to change in a minute. But it's a, let's say, a constant times w. All right. So that means it takes me log w time to find the successor of x in the sample. And then I enter a binary search tree, which takes me another log w of time to find the successor of x inside that search tree. And then the answer is either this one or this, or the successor in here. All right, so, and now what's the space? Well, there's n over w things in here. So its space is n over w times w, which is order n. And then down here, well, there's a list of length n over w. That's not a problem. And then the remaining elements, which is like at most n of them, they're spread across these binary search trees. So that's also only order n. Okay, good. So that, at least in terms of just getting the space down, not worrying yet about insert or remove, this seems to work, and it doesn't slow down the searches by more than a constant factor, because now, in addition to searching in the XFAST tree, you have to do a search in a little binary tree. Yeah.
So the actual size is 2n.
Well, I mean, it's some constant times n, where that constant depends on all kinds of things, like whether or not you store the nodes of this thing, and whether everything is in one hash table or it's spread across a bunch of hash tables. I mean, some constant times n. I mean, it is bigger than just if you had just stored them in the XFAST tree, but oh no, I mean, it's not bigger than that. I don't know. I mean, it's some constant times that. Okay. All right. But now we want to do insert and remove. Okay. So we want to do those things. So let's just do the sort of obvious thing. Let's say that I've already given you this thing, and now I want to insert something. So I want to insert x into here. So I can search for x, and maybe x is already there or not, but if I'm inserting it, it's probably not there. So that search will just give me the successor of x. From that successor of x, there's this little tree here where x should be. X should go in there. Okay. So this is just a binary search tree. I can use my favorite binary search tree that supports adding and removing and log. In this case, it's log w time because it only has w things in it. And I put x in there. So insert x. Now there's one more element in this tree. It's not size w minus 1 anymore. It's of size w. Right? So that's one search up here. That's log w time. one insertion into a tree of size W, that's also log W time. So that's as fast as the search was. All right, good. What about, well, so do you see a problem with this that's eventually going to creep up? Yeah. So if that's all I ever do, then nothing stops me. In fact, if that's all I ever do, then I'm just going to end up with a big binary search tree that has everything and nothing in the XFast try. So in particular, if I just keep inserting things that are around like x, x plus 1, and so on, then I'm getting, this tree here is getting bigger and bigger and bigger. And all of this only works because this tree has size O of W, or at least the log of the size of this tree is O of log W. So I'll need to make sure that the tree doesn't get too big. What should I do if the tree gets too big? So, and what is too big? So let's say too big. That's if its size is 2 times W. So I insert for a while and suddenly this tree becomes of size 2 times W. What should I do? Split it. And well, we've seen nicely, we have treeps. They support the split operation in log their size time, which is going to be log W. Great. So we split. Okay, then what? That's not great so far, because now if I go searching for X, I find this successor, and then it tells me, well, it's maybe in one of these two search trees here, but I want it to tell me it's in one search tree. Yeah. Yeah. So when I split it, in fact, if you remember how treeps work, these things fit really nicely with this. The way a treep, you can do a split on a treep is you take a value, you rotate it until it becomes the root, and then you cut out the root, which is perfect for us because that will split it into two trees, and that one that we took out in the root and cut away, it's not in either of the trees, and so we'll put it into the XFast tree. Now that takes time. I mean, that's not fast. That takes O of W time, the height of the tree. But here's the good news. Well, we haven't looked at everything yet, but what does it do? It takes a tree of size 2W and splits it into two trees. One is of size W, one is of size W minus 1. Before, so these trees now, they're very far away from size 2W. So before I have to ever do this again, I will have to do an insertion that puts at least another W elements into one of these trees. Or another way to think about that is to go backwards and say, well, how did I get up to 2W here? Because at some point in the past, this tree here had size only W. Now it has this size 2W, which means that between then and there were at least W insertions that went only into that tree. And now I'm going to have to spend W time to insert the split node into here, but that's amortized over this W insertions that it took me to make this tree so big. So yeah, every once in a while, and it's not more than 1 out of W operations, will be slow. It'll take W time instead of log W time. But on average, that's only a constant per operation. All right. See any other? Well, okay, so that's how we'll do insertion. If this if one of these bags gets bigger than W, 2W, we'll split it and insert into there. And what about removing? So this now we get in O of log n, which is O of log W amortized time. Because every once in a while there'll be a slow operation. So how about removing? I want to remove something from this data structure. So typical thing is you ask me to remove X, and I go searching for X, and I find it in one of these little binary trees here, because most of the values are actually in these little binary trees. And then I remove it. Log W time to find it, and then another log W time to remove it, using any reasonable binary search tree. Do you see any problems that can develop there? What's that? Yeah, so I could end up in a situation where I completely empty one of these trees. Now, why is that a problem? So if I just emptied one of them, it may not be such a problem, but I could also get into a situation where I empty all of them, in which case I'm now storing whatever my current number n is of elements, but they're all in the XFAST tree. And that's bad news again. So that's one issue. Another potential issue is you ask me to remove X, and I go searching for it, and I find it here in one of these nodes that's in the XFAST tree. Okay. So, what do you do then? You what? Well, no, it's in the XFAST tree, so it's in that horrible structure with all the hash tables and everything else, and this binary trie attached to it. So there's no rotations in that structure. That's an idea, but the problem with that is if I mess with this thing, that takes W time. Right? And so if someone is trying to be nasty and they know how my algorithm works, they'll keep asking to delete things that happen to be in this tree. So that's not great. And unlike in a binary search tree, when you take something away, its predecessor is not a perfect replacement for it. Right? When all you care about is comparisons, that's true. Take something away, its predecessor is a perfect replacement for it compared to everything else. But here we actually care about the bits that make up X. I can't take X plus 50 and just stick it in there and have something that's consistent anymore. Yeah, so if that happens, the trick is you don't take it out. You leave it there, just put a note on it that says, this value is only being used here to separate two bags. It's not actually in my set anymore, so you don't accidentally return it. So that's sort of the easy way to deal with those things. The other issue happens though. These things can start to get really, really emptied out, and in particular, they can start to get too small. And I'll just define too small as W divided by 2. So If there's less than W over 2 things in here, then I'll say it's too small. And all right, what should I do if something gets too small? So it's only got W over 2 things in it. Pardon? Yeah, I mean, now we can do, well, we can do, there's lots of ways to deal with it. But I mean, if this thing is too small and it's not the only thing, so there's always the case where there's less than W elements stored in the whole set, in which case not too much you can do about that. You just have, this thing is empty and this is just a binary tree with at most W elements in it. But I mean, other than that case, when there's so few things, this thing has a neighboring bag. I mean, it has a neighboring thing. And you can just break into some cases. You know, if this is W over 2, and this is, this one here is big enough, let's say bigger than W, then you can borrow from it. So you can then get something like, so in total, this is 3W over 2. You can get at least 3W over 4 and 3W over 4 in each of these things. And that's just a split of this one, and then zipping together the two trees for these things. And that means you make a change up. I mean, the boundary between these two trees changes to some new node, which you insert into this tree, replacing the one that was there. So you can play with the thresholds to get the best thing you want. So that's if this one gets too small and its neighbor is still fairly big. The other thing that can happen is, well, this one is small and its neighbor is also small. And in that case, well, you just merge them into one big thing of size 3W over 2. That's still quite far away from being too big, and it's very far away from being too small. And that requires then that whatever was in the XFAST tree that was splitting these two things, you take it out and you put it into the merged one. So why is all that going to be fast enough? Well, it's for the same reason that the splitting is, the splitting when you do insertion is fast enough. Whenever you have to touch one of these things, it's because you were at some state before which was far from being too big, and then a bunch of operations happened before it became too big again and forced you to split it. And if you look at these rules here, all right, after I apply one of these rules, so maybe it's this rule, then I've created things of size 3W over 4. That's far from W over 2, and it's also far from 2W. So before one of these things needs to be split or merged with something else, there's going to have to be at least W over 4 operations that happen. And similarly, this 3W over 2, it's far from 2W, and it's also far from W over 2. So before anything bad happens here, there would have to be at least W over 2 operations on it. So do this carefully, and roughly something like 4 out of W operations might have to work on this tree, and the rest can live down here. And if you really hardly ever want to touch this tree, you can change the constants, right? You can say too big is more than 50W, and too small is W over 50 or something. You can play with that. Okay, so then you get all these things in inserting and removing in log n amortized time, which is log w, and searches in log w time. So all that to say, looks like it's getting complicated. And it gets kind of complicated, but not terribly so. These rules for splitting and removing, they seem kind of messy and they require stuff. There's actually, if you read the notes, there's a simpler way to do this if you don't mind randomization. And it's just the following. When you insert something, you toss a coin, a biased coin that comes up heads with probability 1 out of W and tails with probability 1 minus that. And if that coin happens to come up heads, then you put the thing up here, the thing that you're inserting up here, and you use it to split something down here. Then you don't have to really, that's the only rebalancing you have to do. So it'll just work out that, well, only 1 out of W things on average ends up in here, which is what you wanted, and only 1 out of W operations, add operations, will cause a split and a touching this thing, which is what you wanted. And what about the remove operations? Well, the stuff that is up here is just a random sample of things where each thing is sampled with probability 1 out of W. So if someone asks you to remove something, the probability that it's asking you to remove something that's in the sample is only 1 out of W, right? Because the thing they're asking you to remove is, well, any particular thing is in the sample only with probability 1 out of W. So it turns out that randomization is probably an easier way to manage these lists than these crazy rules. And you can find code for all this in the notes that are on the course webpage. All right, so that's all I have for you today. Questions?